So, good day to all. Thank you very much for joining us. Welcome to this webinar, jointly organized by the Generation 4 International Forum, known by many as GIF, and the International Atomic Energy Agency. Several joint GIF IAEA webinars have been organized in the past. For this year's edition, GIF, through its Education and Training Working Group, is hosting this online event. The GIF Education and Training Working Group has organized more than 110 webinars since 2016, and I believe that many of you have already benefited from the knowledge shared through previous GIF webinars. Today's joint webinar will focus on advances in artificial intelligence in the nuclear energy sector, with a panel of experts from a broad range of national and international institutions. For those who may not be familiar with GIF, I'd like to briefly mention that GIF is an international cooperative effort that brings together leading countries in the field of nuclear energy in order to coordinate research and development activities, supporting the deployment of the next generation of nuclear energy systems, known as Generation 4 systems. GIF was established in 2001 and is celebrating its 25th anniversary this year. It is governed by an international treaty known as the GIF Framework Agreement, and the Nuclear Energy Agency of the OECD has been providing the technical secretariat for GIF for more than 2 decades. The IAEA does not need much of an introduction, but I would like to highlight that the IAEA is one of GIF's long-standing partners. GIF and the IAEA coordinate and cooperate through dedicated interface meetings, with the IAEA having a special observer role in GIF and its members being invited to participate in many IAEA-led initiatives related to Gen 4 nuclear energy systems. These joint GIF IAEA webinars are one of the concrete outcomes of this fruitful cooperation. Before we start, just a few housekeeping points. Please select the option to use the sound from your computer for having the best audio quality. If you encounter any technical issues, you can consult the Zoom assistance page at the link that is indicated on this slide. And the recording and the presentations of this webinar will be made available on the GIF public website in the days following the webinar. We invite you to share the information about this and upcoming webinars with your network. And lastly, and most importantly, regarding question and answers, you can submit questions at any time during the webinar using the Q&A function. I will show you how to do this in a moment. Your questions will be visible to the speakers and will be addressed after the main presentation. If your question is specifically for one of the panelists, please indicate it at the beginning of your question. So to ask a question, you should use the Q&A button that you can see on the left side of the slide. And once you click this button, a pop-up window will show up as on the right of the slide, and you can type your question and send it to the speakers and the panelists. So thank you again for being so many to join us today. I hope you will find this discussion informative and that you will gain a lot from both the presentations and the moderated Q&A session that will follow. I would now like to introduce one of our 2 moderators for today's session. Dr. Patricia Pavier is the National Technical Director of the Molten Salt Reactor Program at the United States Department of Energy in the Office of Nuclear Energy. So she has more than 30 years of experience that span through actinide and radionuclide chemistry, including the Purex process, waste for development, repository sciences, and molten salt systems for molten salt reactor technologies. So as I said, since March 2021, she has been the National Technical Director of the Molten Salt Reactor Program for the DOE Office of Nuclear Energy, leading and managing groundbreaking research supporting the development of MSRs across 7 US national laboratories with a focus on thermal properties of molten salts, off-gas management, safety, and modeling and simulation. In addition, through GIF, she plays a key role in the global knowledge sharing, having organized and facilitated over 100 international GIF webinars, reaching thousands of experts across 84 countries. Her contribution continues to shape the future of nuclear energy and waste management. And she received her PhD in radiochemistry for the University of Paris-Saclay in France. And Patricia, now the floor is yours to introduce our second moderator for today.
Yes, good morning, good evening, everyone. It's always a pleasure to see so many people following the webinars. We put a lot of effort. We have put a lot of efforts for this one. So it's a pleasure to introduce my, I would say, partner in crime. No, my co-moderator, Dr. Alexei Miasoedov. He graduated in theoretical and experimental physics from the Moscow State Engineering Physics Institute in 1989, and he joined the Kurchatov Institute, where he worked on modeling fission product release from irradiated fuel. He earned his PhD in mechanical engineering from the Karlsruhe Institute of Technology in Germany in 1996, and subsequently joined its Institute for Material Research at the KIT. From 1996 to 2018, his work focused on reactor safety and severe accident research, including light water reactor fuel behavior under severe damage conditions, core melt progression, in and ex-vessel melt retention, and related material behavior. Since 2018, he has served as a nuclear engineer at the International Atomic Energy Agency, specializing in the technology development of advanced light water reactor within the Nuclear Power Technology Development Section, Division of Nuclear Power, Department of Nuclear Energy. So thank you so much, Alexei, for being with us today and for helping me moderate this extraordinary panel. I think we're going to have a lot of fun because AI is a very, very hot topic. So I give you the floor, Alexei, to introduce our first panelist, and I thank you very much.
Thank you, Patricia. Thank you very much for introduction. And hello, everyone. It's my pleasure to introduce the first panelist for today, Dr. Hany Abdel Khalik. He's a professor in the School of Nuclear Engineering at Purdue University and the founder of Covered Defense's limited liability company. He serves as a technical lead of the IAEA Collaborating Centre on Artificial Intelligence for Nuclear Power and directs the SINEX research group at Purdue, where his work focuses on advanced modeling, artificial intelligence, and resilient digital systems. Hany earned his PhD and Master of Science in Nuclear Engineering from North Carolina State University and his Bachelor of Science in Nuclear Engineering from Alexandria University in Egypt. And his professional experience includes academic appointments at Purdue University and North Carolina State University, joint faculty service with Idaho National Laboratory, and industry experience with Arriva NP. Dr. Abdel Khalik's research brings together information theory, physics-informed modeling, uncertainty quantification, and digital twins methodology. His work has contributed to the development of entropy-driven approaches to anomaly detection, industrial system resilience, and secure data architectures, with results documented in peer-reviewed publications and intellectual property disclosures. He has received several recognitions for research, mentorship, innovation, and technology commercialization. It's my pleasure to give the floor to Professor Abdel Khalik.
Thank you, Alex, for the presentation, and thank you, Patricia, for the invitation to this important event. So I want to talk to you today about the Collaborating Center for AI on nuclear power. When people talk about AI, they're usually talking about the flashy things like, it can do better decisions, faster decisions, smarter models, but that's not really what the intent for the center. We decided that somebody has to think about the unflashy things or the not so flashy things, the question of confidence. So you can see the center driving efforts to establish this unseen layer, invisible layer, if you will, that makes AI dependable, that we can rely on it in high stakes environments like a nuclear power energy. So we are not here to add features, but we really want to quietly ensure that the system is behaving correctly, consistently, robustly, securely at all conditions. So what we're building here, you can think of it as a behind the scenes type layer. the easiest way to think about what we're doing is we're not really trying to measuring what the system is producing, but we're trying to make sure that nothing really goes wrong. So we don't want, you hear about biasing, hallucination, things slowly drifting, when you rely on automated decision making, for example. You hear about data being stolen, models being stolen, and intelligence leaking. So we don't want false confidence in the results, and we want to make sure that our intelligence is protected. So think about it as confidence from a safety point of view and also from a security point of view. So if everything is working right, nothing dramatic happens, you really won't hear about us, okay? As you will see, we're driving the research along multiple directions, but a very high level takeaway from this is that we're fundamentally trying to answer the two questions of safety and security. If we were trying to make sure that, if AI is thinking with the right information and it's not being overconfident, not giving you false confidence, it's not guessing. And the other thing is, if the models leak out or an insider stole them, then they cannot really get value from your model, because those models are very, very expensive and they encode the institution knowledge. So think of it as a guarantee layer for AI, not, as I said, not something flashy, not something users will see or interact with. It's under the hood. So from a funny, if you want to think about us, we were not going to announce our successes as nothing failed today. That's the goal, is that if you don't hear about us, that means things are working correctly. So okay. Yeah, let me try to advance the slides. Wait, could you go to the next one? For some reason, it's not going. Okay, so since this started at an academic institution, we are, as I said, we're interested in the validation of AI concepts at the core, but we're an educational institution, so education and training is always a key part of this. And as you will see, we believe that AI cannot just make decision on its own by purely relying on the data. It has to be some thinking, some physics understanding of what's going on. So those are the three pillars of the center. Relying on the physics, we're trying to validate, and we want to disseminate that knowledge to the rest of the world. And I want to recognize Alex. He is the point of contact for this work, coordinating all our activities, helping us set up all these activities at the IAEA side, and I am from the Purdue side. Why Purdue? Okay, for some reason, it's not allowing me to go to the next. Would you please advance?
Yeah, you might need to click on the presentation, but I can advance for you otherwise.
Okay. Okay, now it's working. Okay. So the activities, this is just, I'll let you read this. This is boilerplate language, but we want to publish. We want to support the IAEA mission, obviously, to help the member states adopt this new technology, cautiously and confidently, so that, it does what it's intended to do. And we want to be able to host and interact with researchers and do joint works through coordinated research projects. And we definitely want to do cutting edge research, which matches the mission of the university and IAEA. Okay. All right. So AI challenges. The main issues here are we have a complex decision. I mean, there's so much data, so many models. I mean, you hear about these models having billions of parameters. So how do you make a decision with all those parameters? So complexity is a main thing. And for a lot of scenarios, actually, we have scarce data sources. For some problems, we may have a lot of data, but for some other problems, we have very, very scarce data. And you can always think about scarcity mathematically. How many data points are you going to have at the end of the day, even if you're collecting a lot of data, if you're training models that have billions or trillions of parameters? So mathematically, it's an underdetermined problem at the heart. So you can always assume that these models will be scarce, even if the volume of the data look superficially large. The integrity and the privacy, those are the two other issues that maybe a lot of people are not talking about right now with the rush to adopt AI tools. But we believe, again, as an unseen layer or a guardian of those models, we feel like somebody has to think about those issues. Integrity is the data itself that are being fed to the models. Are you sure those data have not been modified in any way? Researchers have shown that minor modification to the data could have a large impact on these models. And the privacy is, after you learn something, if you've trained your models, you don't want that data to leak out, okay, or the models to leak out. So, because there's intellectual property usually associated with these models. All right. So why do we bring universities here? Because of the R&D, we always like to feel like think that we are on the forefront of solving the difficult problems, but we can't just solve those problems in vacuum. The whole goal is to transport this eventually to the end users, the stakeholders in the government and the private sectors, and we can't do this problem alone. So we really need the help of the people who are building AI. Those are usually considered the data scientists. This new pillar of science that emerged in the last 15 years or so. Right now, the problem is very highly fragmented. Each person is thinking about it from their own perspective. As I said, like data scientists usually think about this as a data science project, a statistical project where they can rely mainly on the data. People who are developing the physics model like to think that they cannot just rely on data models. They just need to rely on physics. So the way we think about it is still fragmented, but in the last 5 years or so, I see more people coming together to try to find hybrid solutions that meet the demands. And the private sector is just watching, some of them have taken a step forward trying to look at the latest, greatest of these model developments, but they're still waiting to see some signs of confidence or robustness before those can be massively adopted. And the government obviously needs to see those measures of confidence before accepting to use them on something that has a big impact like a nuclear system. All right. So why our center? This center, collaborating center, the way it gets structured is that the IAEA finds an already established research center at one of the universities and tries to build this collaboration with. At Purdue, we have this Science of Information Center. It's a 10-year NSF funded, National Science Foundation funded. They have raised over $50 million over the years to basically ask a very basic question. Why do these models work at the core? Okay. And they make a direct analogy to the question that Claude Shannon asked back in the 30s and the 40s. And he laid the foundation for information theory. He's the father of information theory, which revolutionized telecommunication industry. So if you're using a cell phone, you have some tribute to pay to Claude Shannon. So Shannon basically managed to talk about the information content. How much, if you are giving information to two different people, can they drive the same insight from them? And that's the question we're asking for AI. Shannon simply asked about if you are giving the same digits to two people, can they get the same raw information that was submitted? For us, we're asking another question, more difficult question. If we give this data to two people, can they infer or learn the same things? Okay, so that's at a very high level the mission. And because of that fundamental need to understand how AI models, it made sense to establish this center through that center at Purdue University. Okay, so Claude, I invite anybody who's interested in RD aspects of AI to really go back and revisit those earlier paper by Claude Shannon. And at a very high level, we can say that the issues that we're worried about, whether you get overconfidence, bias, etc., is because of two fundamental aspects of information theory: the concept of low pattern encoding, and the concept of entropy invariant transformation. What does those mean? Sorry to get into a little detail here, but I'll do it very quickly. Low patterns, entropy encoding, meaning that you are looking for things that move together at a very layman terms. That can be described by entropy, by a low entropy value. Entropy is just a number. If you find a very small entropy for two variables moving together, that means that's an established pattern. Okay. The other interesting thing about entropy is that it's invariant to the transformation. We don't have to assume a relationship between the parameters. We don't have to say they're moving together linearly or non-linearly, like existing methods would do. No, they are doing it in a very, very transformation invariant approach. So it's independent of the transformation. So because of those two concepts, two theories emerged over the years. This one on the top right, information bottleneck theory, started around 2000, and it's really established the basis for how we can find patterns in the data. The other approach that cannot call it theory yet is the concept of communication mule, that we believe that this Gen AI tools that are being developed right now can be used as a perfect mule for transforming data or for transmitting data and for computing in a secure way. So those add the high level questions or directions that we are going along. Okay, so if we go one level deeper, we are trying to establish expertise in those 4 different areas. Pattern recognition, synthetic data generation, those are following the first theory that I mentioned, which is the bottleneck theory. How do you define the patterns confidently, and how do you use those to generate data that look normal and matches all the success criteria of what the data should contain. And it has the right inference information about what the quantity of interest you're after. The other two, which is the mule idea for AI, is we use it for data masking so that people can confidently work with the private data without leaking, and self-awareness. If the data get tampered with, their integrity is in question, they can recover. The overall goal is to have a platform online where we can work together on benchmarking these tools. We can iterate until we find methods that are confident and robust that we can use. And we can use this to explore basically our goals, our ultimate goals. How do we improve our experimental models? How do we improve our experimental setups, our physics models? And generally, that supports, the development of validation techniques for neural systems, accelerate the licensing, all the list of demands that we love to have out of AI in support of existing and advanced reactors. Okay, so I'll just give you maybe 30 seconds examples of things that we've done over the last few years, so you can get an idea about the activities, and hopefully encourages you to reach out and do some collaborative work together. This one was set up through OECD-NEA, but it was also something that we did through the center, where we basically pulled people from all around the world. We had over 30 participants, and we set up a really basic benchmark problem, a model with 5 parameters, as simple as 5 parameters. And we relied on a simple linear model, and then maybe a quasi-linear model and a nonlinear model. And we asked basic questions. If those input parameters have errors, how do we fix them? We need to build experiments, to inform on those parameters. And the question is always the coverage. Do we have enough experiments to cover the uncertainties that we have in this data? So the concept of error recovery was key to this work. And without going too much in detail, these are the 2 papers that you can find out on the results of this work. And we still have another paper that will in the pipeline that should go out this year. The key findings is that existing methods, when provided with the right data, they succeed. Okay. Any of the methods out there, if implemented correctly and you provide it with the right experimental data, it always gives you reasonable results. The problem is we are set to ask the question, how do we select the experimental data that we actually need to complete validation, for example? So the 2 failure modes that were identified is that a lot of data that are currently being deemed relevant could actually be redundant. So they don't improve your predictions at all. You keep adding them and your uncertainty still remains the same. The other thing is there are a lot of data out there that are deemed usually less relevant, or they can be discarded, and they have a lot of value. And those are the exact data that you need to include to improve your inference. We built a pipeline around this, and we already have some website interfaces that we're happy to share with you guys to answer that question of coverage. Okay, and turns out if you want to do that, you rely on a lot of typical mathematical techniques that can be encoded with AI, starting from reduced order modeling approaches, determining features, determining a surrogate model, or in information theory, we call it kernel mapper, and eventually you can use that to generate data. But at the center of all these activities is the concept of coverage that we believe is needed to say whether an AI model is presented with the right data. And if it's not, then you should have less confidence in the predictions that it makes. So we have multiple projects that we're set to basically discover this, including fuel irradiation problems, facility models, radiochemical assay type measurements to try to understand how a nuclear fuel has been irradiated. So lots of applications. I'm happy to go into details with you as interest develops. Okay, so this is an example of work that was done, for example, with a nuclear fuel vendor, where we have operating data with uncertainty, that's shown by the red cloud. And then when you use these methods, that rely on entropy, then you can get an estimate of, improved estimate. But the more important thing is that you get that green cloud. That gives you an estimate of your confidence, how much confidence you should assign to these data. And again, there's some paper here that you can look up for some of the initial results. Okay, we also use this to help improve experimental design for shipping material. That's an application that a lot of people are interested in right now with the expanded use of nuclear power. So after the fuel comes out from the reactor, it goes in a wet pool and then dry storage. You are thinking about shipping it somewhere. Then, or you are talking about new fuel that's coming for new reactors, needs to be shipped to the reactor. So how do you design shipping containers for them and make sure that they are critically safe? So you want to design an experiment that's as similar as possible to that application. So question is always, how do you decide on similarity or relevance? And we showed that if you rely on that CK approach, which is the current approach in criticality safety to determine similarity, you get different results than if you rely on this information theory approach. In fact, it turns out that you get better optimized solution that costs less. So that's an eye-opener for the fact that maybe these failure modes I talked about earlier, when you think something is relevant, maybe it's redundant. And when you think something is irrelevant, there might be some information that can be teased out to improve your inference. This is another application. So I am running out of, because of my academic hat, I could easily run out of time. How much time do I have, Pat? Maybe 5 minutes or less?
Yes, 5 minutes.
Okay, all right. I'll try to wrap this up under 5 minutes. So this is another application that also shows the success of these methodologies. We had two different labs that we worked with, one in Europe actually, and one in the US, that tried to estimate the burnup for a fuel that came out of a reactor, and they were off by almost 50%. Okay. And we use these methodologies basically to confirm which one is the correct one. So again, this shows an direct value for these confidence estimates to try to pick what would be a right solution. So it could be an arbiter basically, or a validating approach for all these AI driven tools. We use this also to improve nuclear data, and we asked from this new perspective of information theory by asking the question, the existing experiments, how much coverage they provide for, let's say, for a cross-section of maybe plutonium-239 fission cross-section at a certain energy. This is the uncertainty before, or actually this is the QC, which is the coverage. 50% of the initial uncertainty can be removed using the existing data. Then you can ask yourself, is that good enough or not? But having this metric, that agnostic metric does not really care about the inference method that you used or the regression technique that you used, and gives you just one number, can provide a lot of value to experimentalists and also modeling and simulation folks. And we're seeing that this could be an established approach for judging, the quantities of interest for reactor design and also for regulatory purposes. Lots of different applications. Now I said a lot of stuff on the first goal, which is the bottleneck or the low entropy. How do you establish confidence? I want to say a few things about the security side of things. These technologies can also be used to do this concept of data devaluation. We're calling it inner-doxing, similar to concept of paradox, like encoding in false appearance, so that the data that are leaked, whether wittingly or unwittingly, can be devalued. Okay, you invest a lot of money into building these models. You want to make sure that they don't get leveraged against you or exploited for malicious use. So this technology can be used, if again, through the lens of entropy, you can use it to devalue the data. Because of this second feature of entropy, which is the invariant to the transformation. So if you give me data that look like a nuclear reactor data, using a mathematical transformation, I can turn it into something completely different. Okay, I can take maybe nuclear data and turn it into something that looks like musical notes, but it has still the same information content. But to a reverse engineering person who's trying to, guess what your system looks like, it becomes near impossible to do that. So devaluing the data that got stolen can be used to do also deepfake detection. Talked about the integrity issue. So if data are being modified, how do you ensure that you can detect that, and you can protect the privacy of your data while you are doing AI model training. Okay, so I can stop here, and I'm happy to take questions. Thank you very much.
Yes, thank you very much, Hany. We will take the question at the end of the 3 talks. It will be much easier. And again,
yes, of course,
for the audience, please write in the question box the person you would like to ask the question to. It will be easier. And if it's for everyone, you just put to all. Like that, we will know as moderators how to do. So thank you again, Hany, for this very comprehensive presentation. And it's my pleasure now to introduce our second panelist, Mr. Shahab Dabiran. He is a nuclear scientist at the OECD Nuclear Energy Agency in Paris, where he supports international research on advanced fuel cycles and supports collaborative technical projects on topics such as fuel cycle closure and artificial intelligence. He has over 14 years of experience in the nuclear industry. Prior to joining the NEA, he spent nearly a decade at Ontario Power Generation, supporting the Pickering and Darlington reactor physics teams, as well as the Darlington refurbishment return to service projects, where he contributed to reactor physics commissioning tests. While at OPG, he developed multiple tools using data science, machine learning, and AI to enhance core surveillance, fueling strategies, reactivity management, and fuel defect identification. So again, my pleasure to have you here, Shahab. I give you the floor, and thank you again for accepting to present and participate in this GIF IAEA joint webinar.
Thank you so much, Patricia, for the kind introduction. So as Patricia mentioned, my name is Shahab, and I'm going to talk a little bit about some of the work that we're doing, both supporting advanced fuel cycles, but also AI, machine learning, and nuclear research at the OECD-NEA. So the team that we work on some of the expertise AI projects is our division head, Tatiana Ivanova, Oliver Boos, Kenta Inagaki, and Annabelle Sanders. So in terms of a bit of an outline for the presentation, I'll give you a bit of a background on OECD-NEA and what we're about, and then the work that we're doing in the space and domain of advanced fuel cycles, and then move on to the main topic, which is AI and machine learning, both ongoing activities and some of our plans as we go to the future. So the NEA itself is composed of 34 countries, and these 34 countries account for approximately 80% of the world's installed capacity. The way that we distribute the work is through 8 standing committees, many working parties and expert groups. And of course, we have the NEA Data Bank, which provides nuclear data, codes, and verification services. many international joint projects, which includes the AI Expertise Joint Project, which I'll talk about in this presentation, and of course, a growing global relationship with both industry and academia through universities. So the way that we break the work down, starting from the top, we have the Steering Committee for Nuclear Energy, which is composed, as I mentioned, of 8 standing committees covering topics everywhere from regulatory services, nuclear safety, rad waste management, decommissioning, radiation protection, nuclear law, nuclear technology and economics, and of course, Nuclear Science Committee. And under the Nuclear Science Committee, we have the Division of Nuclear Science and Education, where a lot of our work is done. And under this division, we cover everything from reactor physics and transient studies, radiation shielding, fuel cycle physics and chemistry, which I'll talk a little bit about in this presentation, all the way down to nuclear knowledge management, education, and training. And we do so through the contributions of our thousands of international world-renowned experts, through multiple working parties, working on databases, benchmark studies, publications, workshops, joint projects, and of course the Global Forum, which I'll discuss also a bit as we go through. So, advanced fuel cycles, and what are we doing in this space? In the NSC, all the work on advanced fuel cycles, most of them anyway, are done under the Working Party on Scientific Issues of Advanced Fuel Cycles. And you can use the QR code here in the center of this circle to access our website, where we have lots of our ongoing activities, in addition to a lot of the publications, which I'll discuss in this presentation. The work we do in the Working Party, the WPFC, is split into 4 expert groups. We start with the EGIF expert group on innovative fuel elements, which focuses on innovative fuel designs, fabrication and radiation, of course, international collaboration and advanced reactors. We have the expert group on reactor coolants, components technology, e.g. COCOT. This group focuses on advanced coolants, mainly sodium, lead, and lead bismuth, eutectic, and components. We look at material and components evaluations, safety performance, and of course, all cross-cutting research on these as well. We also work on expert group on advanced fuel cycle scenarios, e.g. AFCS, which, as the name suggests, does a lot of analysis on long-term fuel cycle decisions, resource optimization, scenario modeling, and ultimately supporting decision makers and policymakers towards the strategy that they choose for their fuel cycle as they go forward. And last but not least, the expert group on fuel recycling and waste technologies, EGFRW, which focuses on fuel recycling, waste management, process optimizations for all different types of reprocessing, and international best practices as well. So to look at a bit more detail of these expert groups, I'm not going to go into crazy detail, I'll keep it a bit high level, but as I mentioned, all these reports that you see on the right and many more are available on the WPFC website. So if you need a good bedtime read, please feel free to access these. In terms of scope, as I mentioned, the group, the EGAFCS, focuses on analyzing different scenarios to assess the potential different options of fuel cycles and how they impact the downstream. It's also their uncertainty that's associated with these choices. And we look at the needs and the requirements that are associated for different states to transition from their current fleet to more advanced nuclear fuel cycles. And this is using their existing, but also future technologies, which can include transmutation and storage technologies as well. In terms of current initiatives, we're a few weeks away from publication of this very interesting report called Harnessing International Cooperation for the Management of Transuranics. And here we're looking at scenarios where countries are, as I mentioned, transitioning to advanced fuel cycles, and particularly a case where one country is phasing out nuclear and another country is phasing in advanced fuel cycles, and how this kind of cooperation can support the deployment of these advanced technologies and the management of the transuranics. We're also working right now, or beginning the project on evaluating fuel cycle options for tripling nuclear by 2050, which looks at the front end and back end and economic impacts of different fuel cycle choices as we look to triple our nuclear by 2050. And development of portable surrogate neural networks. So this one now ties into some of the machine learning activities we're doing, where different fuel cycle scenario codes have modules that perform depletion and irradiation calculations. These are often quite time intensive, compute power intensive. So we're working towards developing portable surrogate neural nets, which can be placed into different fuel cycle scenario codes and support their depletion calculation modules. Next up, we have the eGIF group. As I mentioned, this group looks at advanced and innovative fuels. In the past, we've looked at all different types of fuels, such as oxide metals, nitrides, carbides, and special mechanical forms, specifically for the use in Gen 4 systems. And we look at currently now looking at performance and properties of fuels dedicated to minor actinide transmutation for advanced fuel cycles in Gen 4 systems. And now we're looking again kind of more focused towards oxide and metal fuels at this point. Some of the reports you can see on the right, we did already some benchmark studies with fuel performance codes on fast reactors, and then a recommendation of fuel properties as well. So now we're continuing these activities in the second phase of the benchmark, which should be published a little bit later this year, followed by continuation of the effort to standardize advanced fuel properties for fuel performance codes, which is quite an intensive challenge and very important as we go towards qualifying new innovative fuels. EGFRW, the expert group on fuel recycling and waste technology, as I mentioned, looks at recycling and the separation processes that are relevant to recycling technologies, including different types from aqueous to pyro, different waste treatments, recycling and reuse of spent components. We recently published in 2025 this very interesting report on unlocking hidden value of nuclear fuel, which looks at the extraction of elements and isotopes from spent fuel that are not just for the fissile material, but also for applications in the medical industry, space industry, and the recovery of platinum group metals, rare earth elements. All these are very important for the industry, and the different techniques to be able to extract them from spent fuel. And we're also working on developing and maintaining this international database of extracting ligands, the IDEAL database, and working with our good colleagues on conducting critical evaluation of fuel management during and after MSR molten salt reactor operation, which is very conveniently abbreviated as CREAM. And this, as the name suggests, looks at supporting the deployment of MSR reactors as we go forward. And finally, the EG COCOT group looking at lead bismuth, and sodium coolants and their effects on components such as structural materials. We look at also chemistry control, the different types of thermohydraulics considerations that we have to have for these advanced coolants, components behavior, safety issues, codes and standards. And our current initiative is essentially updating the 2015 edition of the Handbook on Lead and Lead Bismuth Eutectic, Alloy and Lead Properties, Materials Compatibility, Thermohydraulics and Technologies. This is a very major and important publication for the developers of these advanced reactors, as it is used for a lot of the safety analysis and regulatory review for these developers. So now on to the main matter at hand, our AI and machine learning activities, some that we have already ongoing. In terms of the overall OECD-wide activities, we have the OECD AI and Global Partnership on Artificial Intelligence, GPAI. These are more high-level, looking at the impacts of AI on policy, economics. But when we focus down to in the NEA, we also have multiple activities. Two joint projects, which I can mention, is the NEA project on nuclear safety RegLab. This is an exercise that looks at sandboxing exercise, my apologies, with cooperation between EPRI and IAEA and NEA, of course, where regulators, developers, and industry folks are in a room, in a safe space, and they talk about the challenges towards the deployment of AI on all sides, industry and regulation. And of course, the NEA expertise project, which I'll talk about in my future slides, looking to develop an AI platform for research and education. And we have multiple data preservation projects and benchmarking exercise, which I'll talk about in my next slide. So in terms of these ongoing activities within different working parties, some which were already alluded to in Hany's presentation. The critical heat flux AI machine learning benchmark, this is an ongoing benchmark in the reactor systems working parties, a working party on scientific issues and uncertainty analysis of reactor systems. And this is already well underway, looking at a way that we can use and leverage machine learning techniques to replace or improve some of the lookup table work that is currently done to do CHF, and also interpretation, classification, and prediction of time series data from research reactors. This is another project that will be taking place in this working party as well. On the material side, the WPFM, which is the Working Party on Material Science Issues in Nuclear Fuels and Structural Materials, this group is working towards a large review of current applications of machine learning, AI, and uncertainty quantification, specifically for scale bridging, multi-scale simulations, so from atomistic scales also all the way to engineering scales to support fuel performance. And so this is an incredibly important work, and we're looking forward to that publication relatively soon. And then in the criticality safety group, we have the data assimilation and benchmark for error recovery, and quantification of experimental coverage. Again, very important work that's looking to expand some of our validation domain for areas with poor experimental coverage. And so this helps us essentially identify benefits for research and development. It's helped us identify and mitigate some of the regulatory hurdles in this domain. And what we learned from these, and I can go into my next slide, from these projects, in addition to a lot of the surveys and bilateral meetings, attending the different Reg Lab meetings in this past year, essentially, and the very important trilateral paper by 3 regulators, the Canadian regulators, CNSC, ONR from the UK, and NRC, which looks at considerations for developing AI systems in nuclear applications. We essentially put together this narrowed down list of requirements for industry-wide AI machine learning deployment, which is 1, collect and standardize data, very important. Invest into verification and validation of AI/ML to increase its trustworthiness. Assess AI predictive powers and their application domains, and develop experience and hands-on training for users of these AI and ML applications. So putting all this together led us to develop the program of work for the Expertise Joint Project. So the AI Expertise Joint Project is a project that's looking to harness the potential of AI and ML, and it's looking to first demystify a lot of these AI solutions and be able to harness their power in a very defensible way. And why we need to do this now is, first of all, these technologies are starting to be deployed in industry, in utilities, in academia, of course. And so we need to keep pace with this kind of very fast advanced space. And we need to ensure the readiness for regulatory review for a lot of these approaches, and of course support their innovation in operations and potentially other things such as SMR deployment. And how we want to do this is, firstly, establish a community of practice, bring together all experts from around the world that are working on these tools in different domains, in different backgrounds, with different backgrounds, to come together and develop very structured deliverables that can help the industry as we go forward. How we want to do this? So we split our activities into 3 major pillars, as I mentioned, based on the needs. First pillar is the focus on data and developing data sets for AI applications specifically. And in this domain, we have more than 40 years of experience at the NEA in preserving and disseminating experimental data in various domains. Then we need to test all these different algorithms in these different application domains, and that's going to be done through large benchmarking exercises. So it's essentially looking to build a bridge between nuclear and AI domains to advance this expertise. Again, in this domain, the NEA has tremendous experience. Very recently, with application to AI, is a task force on AI and machine learning for scientific computing, as I mentioned, which is working on the CHF calculations currently. And for disseminating knowledge and training, we have more than 20 years of experience here to provide hands-on training on the use of AI algorithms for nuclear research and education. And we want to put together this online platform for everyone to collaborate and bring their aggregated data sets, benchmark specifications, software, AI models, and etc. So to get a bit more detailed into each pillar, starting with the data pillar, if I can draw your attention to the pyramid on the right, this is essentially a way that we can use to evaluate where data sets are as they stand. Starting at the very bottom, which is the generation and collection step, and then organize, store, define licensing conditions, evaluate data in these to make sure they're high quality and peer reviewed, and then develop metadata, which can be used by application programming interfaces for a lot of machine learning and AI applications. Ultimately elevate them all the way to the findable, accessible, interoperable, and reusable standard called FAIR. And this can help us ultimately perform data mining, provide new data sets, flag inconsistencies and outliers, and ultimately be able to extend and implement continuous testing and improvement strategies for many of these data sets. And what this looks like very specifically, and I apologize for this table, it's pretty crowded, but essentially the first 6 data sets that you see on this table, and I should say this is like a menu of activities that we're proposing to take on in expertise, and it would look something like that, where the 6 top data sets are maintained at the NEA, starting with very important ICSBEP, the Criticality Safety Benchmark Evaluation Project, the Reactor Physics Experiments, IFPE, which is the Fuel Performance Experiments, SF-Compo, of course, International Assay Data of Spent Nuclear Fuel, SIMBAT, Shielding Integral Benchmark Archive, and finally, very important, Halden Reactor Project Legacy Database. And you can see the domains that these covered so wide, starting from neutronics, reactor physics, fuel performance, shielding, multiphysics, so it's just covering a wide array of studies, and where they currently stand in terms of their data sets, again, is quite diverse. We have everything from data sets that are already have graphical user interfaces. They have relational databases already with lots of evaluated metadata, and some which are a little bit lower on the scale, for which there's already licensing conditions. But we want to elevate all these to the final step of in the FAIR standard, let's say. And then for the Halden, it's currently in the generated stage, and we want to upgrade that also towards the evaluated data and metadata so we can investigate it in a much more efficient way. The last 2 are data sets that we look to bring into the project. So we're not just working on data that exists, we also work with data that will be provided by utilities, research reactors, thermohydraulic loops, and etc. And we want to support these as well to elevate them to higher standards. So in terms of the benchmarks, once we have the data, we're going to work on essentially these concepts of collaborating amongst industry, research, academia, and very importantly, regulators. We want to evaluate the performance of these of these algorithms to demonstrate their performance, their explainability, and robustness. We're going to train new AI algorithms for some of these challenges and ultimately develop these best practice guidelines that will be used as deliverables for the industry to use to know which algorithms work best and for which domains. So some of the examples, I'm not going to go and read through them all, but you can see again the domains and the goals that we're trying to do, extend the validation basis for field performance through work on the Halden. If we want to bridge the gap of validation, we can look towards fostering verification, validation, uncertainty quantification algorithms for advanced reactor designs. Nuclear science chatbot is another one which has enormous interest amongst the participants. Applications towards thermohydraulics, again, multi-scale integration for fuel materials and PINs, physics-informed neural nets, all have enormous interest and enormous potential for deployment in the industry and research. So we look to support these at the interest of our members, and more in the domain of scientific computing. But I want to bring your attention to numbers 9 and 10, which is health monitoring of reactor operations. So this brings us back to industry and utilities to support them through things like reactor time series analysis, which helps us classify different events, time series forecasting, and of course, optimization of nuclear power plant core reloading patterns. So through fueling for different types of reactors, PWRs, BWRs, CANDU reactors, what have you, to ultimately support the optimization of nuclear power plant operations. In terms of education, we look to offer resources for training. We will be working with many universities and training centers to organize workshops for sharing best practices, also organize potentially AI and machine learning schools, and develop and implement potentially a certified education program through our partnership with the Global Forum, which is one of a kind in terms of science technology policy on an international scale. And all of this will be done to support the nuclear workforce development and support this continuous learning in this space, which is going to be very important as we look to deploy these tools. So I'm not going to, again, read through all these, but we've had lots of very interesting ideas for different workshops and trainings and lots of different interests from different organizations. You can see the range of interests, everywhere from Framatome, University of Liverpool, CNL, which is Canadian National Labs, Imperial College, and so on and so forth. A wide range of backgrounds from industry, utility, and academia and regulators, which are very interested in participating and supporting this joint project. So being a joint project means that the participants will have to be contributing in some way or another to the project once they join. This can be contribution through computer resources, hosting events and training, sharing existing tools or software, providing hands-on training lectures, providing financial and staff support, or sharing relevant data sets. So on the preliminary budget estimate, so we expect financial contributions depending on the nature and size of the organization, and of course in-kind contributions. And the financial contribution will be, going towards very specific needs like hiring data scientists, maintaining the IT platform, and covering the secretariat support. So in terms of timelines, as I said, it's been more than a year of work to put everything together. And we're hoping that by June 2026, we'll be launching the project with our membership and begin kind of prioritizing some of the tasks in the menu that I shared with you from the data, the benchmarking, and the workshops and training. All will be prioritized with our management board that will be the participants into this project. So with that, I'd like to conclude. The expertise program of work is now in a mature state, and we expect prioritization by the management board shortly. You can still join the project. You can scan that QR code to get more information through the expertise website. And if you have any questions after this, we can, of course, take it to our Q&A session. But if you'd like, you can also send us an email in the mailbox below, expertise@oecd-NEA.org. And with that, I finish my presentation. Thank you very much.
Thank you, Shahab, for this interesting overview of the OECD-NEA activities in support of AI deployment and development. Just a reminder, put your questions in the Q&A, and we will address them at the end of the presentation session. Please allow me to introduce our third speaker, Dr. Pavel Tsvetkov, who is a professor of nuclear engineering at Texas A&M University and director of the graduate program, where he leads the Advanced Energy Systems Laboratory. And his work focuses on AI-enabled design, intelligent operations, and advanced reactor and fuel cycle technologies, with applications spanning nuclear security, autonomous instrumentation and control, waste minimization, and resilient energy systems. He's an active contributor to national and international nuclear security efforts and leads the Data Science and Digital Technologies Thrust within the National Nuclear Security Administration Consortium for Enabling Technologies and Innovation. Dr. Tsvetkov has an impressive record of more than 300 peer-reviewed papers, conference proceedings, and technical reports, and has served as editor of major contributor to 15 books on energy, environment, and nuclear engineering. He holds multiple patents in advanced reactor technologies. His professional service includes leadership roles such as chair of the American Nuclear Society Reactor Physics Division, associate editor of the ASME Journal of Nuclear Engineering and Radiation Science, and current vice chair of both the ASME Technical and Strategic Advisory Board and the A&S Publication Steering Committee, as well as chair of the A&S Book Publishing Committee. He continues to serve on the A&S Reactor Physics Program Committee. And please, Pavel, the floor is yours.
Thank you very much, Patricia and Alexei, for setting up this workshop and for having me as a speaker here. Great presentations, and I learned a lot. I'm glad to be the final speaker on this. Let's hope I can advance. Yeah. At Texas A&M, in our research efforts, we look at integrating AI and machine learning-based solutions into reactor design, look into expandable applications that would benefit from use of AI for both terrestrial and deep space domains, look into integration of AI for system optimization, operational safety. It extends to a broad range of interdisciplinary collaborations to support all of these efforts as well. This workshop is very timely because certainly, as speakers before me already indicated, nuclear is gaining momentum, and there are about 100 plus startups globally. There's a surge in application activities for licensing, covering essentially all conceivable reactor types. And that requires to be smart about designing these systems, evaluating what these systems actually bring into consideration, and how we identify what would be safety concerns. Every major nuclear accident was a learning experience for the community. And frankly, at the same time, engineering community was surprised every time. So we learn something new every time, and that's how we learn and advance engineering design. To avoid learning from accidents, certainly deploying AI and AI-based solutions appears to be quite beneficial, and we're looking at taking advantage of that. Saying all of that, there is certainly industry bottlenecks. There is an ambition to advance nuclear, but infrastructure is limited. There is certainly design space complexity. Most of the Generation 4 designs, if not all, frankly, offer extreme environments and quite unique fuel forms and materials that challenges traditional analysis. PRA, fault trees, other methods certainly challenged by that. There are certainly limitations of the physical test beds available for testing and qualification of these systems, exploring what performance domains may look like. And of course, timelines for licensing and evaluation, especially if you count in new fuel forms, new material forms, is quite challenging and extensive. When we look at energy development, certainly we can identify at least three components. And for the purposes of this talk, let's look at them as energy triad, looking at balancing demands of modern nuclear power, and at the same time identifying supply needs, identifying economics, taking care of nuclear waste, looking at how would this can be optimized for a commercial competitive domain where multiple vendors would thrive and perform well. AI appears to be quite a useful tool in that regard, providing advisory and development role for vendors, regulators, and also for the community to assess what might be a suitable technology to deploy. In our efforts, we have a variety of projects focusing on a broad range of nuclear reactors. Early on, when I started in nuclear engineering at Texas A&M, high temperature reactors were quite popular, and very high temperature reactor was a front runner at that time. We continue those efforts. We advance collaborations with vendors pursuing high temperature reactors today that resulted in a variety of integration efforts of high temperature reactors for process heat application, for waste management, and beyond. And certainly, considering extreme conditions, materials needs for high temperature reactors, deploying AI solutions in the design development becomes quite an attractive tool. That being said, all of you probably have heard at this point efforts in Texas by vendors like Fermi Nuclear pursuing deploying AP1000s together with contemporary energy sources like gas and renewables to support data centers. That leads to large power plant systems like AP1000s operating together with a variety of very diverse energy sources, and the need for integrating all of that together with data center related technologies. That's a quite interesting effort, both on the system side and design side, that we are very much interested. And of course, we're building molten salt reactors together with Georgia Tech and University of Texas and Abilene Christian University, funded by natural resources. Texas A&M is assisting natural resources to bring a molten salt reactor to Abilene Christian University. Very interesting effort and very challenging effort because we had only one molten salt reactor operated by Oak Ridge National Lab quite a while ago. There's a lot of efforts initiated and led and chaperoned by Patricia to make molten salt reactors possible, to gain data needed for molten salt reactor evaluations. And AI and predictive engineering certainly a significant necessity to facilitate that and make sure that this type of systems can be brought into operation sooner than later. And of course, there's a paradox as far as AI deployment is concerned. We must use AI and generative AI in particular tools to accelerate nuclear system development and nuclear engineering. And at the same time, nuclear power does come as energy source needed to support generative AI and advances made by generative AI. That's quite unique, and it's quite interesting to see how this is unfolding. There's a paradigm shift from legacy physics to digital core, as I would call it. When we're looking at still traditional needs, we're looking for coupling and neutron transport and thermal management in integrated solutions. We're looking at core visibility and uncertainty. We're looking at operations and control. We're looking at integrating humans in the loop in a variety of ways, instrumentation and control, human-machine interface, all of that. And that certainly very difficult to do using traditional methods. And shifting to digital core, looking at development of core configurations, power unit configurations, taking advantage of agent-based solutions to explore performance domains and identify what would be a safety concerns becomes quite paramount. As I said at the beginning, we're hoping that with AI, it will be possible to design out most of their potential adverse safety scenarios and minimize chances or eliminate chances to be surprised. It's an accelerator for us as far as AI-based technologies. What used to be taking months in development and sequential calculation now takes minutes to produce and perform studies in parallel in integrated fashion and analyze data in a multimodal domains in a very, very efficient way that were not otherwise possible. We also can supplement scarce and limited data domains for advanced reactors, and look into taking advantage of AI solutions of extending data ranges where original data sources may not be present. There is certainly interest in autonomous anatomy of these advanced reactors, looking at cyber-aware operations. Speakers before me pretty much all mentioned the need for cybersecurity awareness of how we would do that. Employing AI for these applications requires special sensitivity in how we gather data, how we train AI-based solutions on the data sets. But at the same time, we certainly take advantage and have been quite successful demonstrating that AI methods are quite efficient at anomaly detection and supporting autonomous operation of the systems. At Texas A&M, we used our trigger reactor for that purpose, and our simulator laboratory to extend that to advanced reactor designs as well. And this is very synergistic, as I will mention later, to efforts funded not only by Nuclear Energy Office of Department of Energy and vendors commercializing reactors, but also funded by National Nuclear Security Administration as part of consortium model. We're part of the Enabling Technologies and Innovation Consortium led by Georgia Tech. Dr. Erickson is the director of the consortium, and through that consortium, we exploring how would that be possible to use AI and machine learning methods to support autonomous operation of advanced energy systems. With that, we certainly extend to human-machine interfaces and figuring out how would one put together instrumentation and control room design for such a novel systems as molten salt reactor, and how we do that in a way that would facilitate operator performance in those novel systems. Digital twins is on the mind of everyone in nuclear engineering, and digital twin certainly synergistically integrated to AI-based solutions. We have successfully attempted and demonstrated that, yes, in multi-modal telemetry domains, integrating different data streams from a variety of measurement systems can be quite successful and beneficial. And those large data streams may involve information from satellite platforms, for example, for microreactor observation and control. It can be a mixed field reconstruction for in-core anomaly detection. It can be used for calibration of some of the digital instrumentation systems. It can be support for autonomous operation of all of that in microreactor domains. And that brings AI to forefront of this. And in every project, we see more and more expanding role in advisory status at this point. But we're learning how to box AI solutions and make sure that training is done responsibly in those instances when data need to be secure and proprietary nature needs to be accounted for, and accounting for multimodal data streams in experimental environments, and synthesizing both computational environments and experimental environments as well. Gen 4 reactors exist mostly in development domain. They don't exist yet in real domain. And as a result, we have to look at demonstrating performance of those systems in computational solutions, looking into demonstrating their performance using existing research reactors. And we have done that using a trigger research reactor at Texas A&M and other reactors as well. looking at materials development and looking at synthesis of materials for these emerging systems that will endeavor high temperatures, very extreme environments from a corrosion standpoint. Also, synthesis of the materials. Molten salt reactors in particular are quite interesting because a reactor allows you to synthesize a fuel mix close to real time, if not really in real time, optimizing reactor performance and extending from optimization of reactor performance for operational objectives, but also to, for example, minimize nuclear waste. So that's quite interesting, and it's very, very suitable for AI applications. Cyber physical security, I already mentioned our efforts in that area. Certainly system surveillance, certainly cyber physical domain in the fuel cycle, facility solutions in their observation, extending to satellite-based platforms to provide means to support microreactor operation in various environments. It's quite challenging, and AI does come quite efficient to the rescue, looking at offering effective solutions. It's a paradigm change, and we're moving certainly from physical constraints to digital agility to make sure that this is possible. Going through the entire cycle, from development to licensing to operation, decommissioning certainly is quite important, and then controlling what goes into disposal and how we develop those mixtures that ultimately go through the entire life cycle of the plant and ultimately goes into a repository. From AI development perspective, integrating human into the loop is still necessary. And I'm telling students that in nuclear field, there is certain job security for humans. I think AI, as smart as it gets, will always be an advisory resource and development tool, but humans certainly will come always as part of human AI synergistic collaboration. Looking at the engineering side, physics, data science, policy aspects to accelerate deployment timelines. AI also is a de-risking tool, looking at how would you leverage existing hard physical infrastructure, efficiently utilize test beds, and extend what's available from reactors that's operating today to simulator-based solutions that allow us to test what reactor will not be able to help us to test. In the university environment, there's a synergy that's quite unique because we're capable to meet industry needs in quite challenging research endeavors and facilitate commercial deployment, serve as an incubator for novel technologies, and at the same time, de-risk those technologies in research efforts, supporting commercial vendors. We can identify two pillars. One is de-risking and bridging the gap from this pillar one to student workforce and making sure that we are introducing a highly specialized and at the same time trained and multidisciplinary workforce that can take advantage of emerging technology solutions. We like to develop a bilingual nuclear engineer who would be comfortable with traditional engineering methods and at the same time will be able to take advantage of advanced AI-based solutions, looking at integration of hands-on experience, industry integration, and novel pioneering solutions that is being developed in a university setting. With all of that, being at university makes it quite unique because we can do it all and we can provide these experiences for students that allows them to take all of that to commercial domains and work productively for all of those emerging vendors, and also potentially become one of those emerging vendors as well in all of the domains for terrestrial applications and space applications as well. We graduate about 200 graduate students, about 400 undergraduate students at Texas A&M in nuclear engineering, with essentially one comprehensive goal to introduce capable workforce and cultivate today engineering workforce that can meet demands of expanding nuclear development and be capable to utilize emerging AI solutions efficiently. We're introducing foundations. We certainly provide environments that students will be able to learn and master those skills and then be introduced to potential opportunities. There is certainly interdisciplinary convergence. We look into novel emerging technologies beyond AI and taking advantage of AI. I would claim there is no project today that doesn't use AI to deepen discovery and amplify impact. It's an exciting time for nuclear to do that, and we can do it faster with AI methods. With that, I like to acknowledge my capable team of graduate and undergraduate students. We certainly wouldn't be able to try and explore this all if not our students. And this is true for everybody at universities. And certainly special credits go to Mr. Watson, who is my champion in my team for everything related to AI, and to Dr. Erickson and her leadership in ETI consortium, enabling us to try AI methods in a variety of domains to secure advanced nuclear reactors. With that, I'd like to thank everybody for listening, and I'm looking forward for a discussion and questions.
Thank you. Thank you for these three very interesting presentations. And just before we move to the Q&A session, so reminder to everyone, please put your questions using the Q&A pane at the bottom of your screen. And if the question is for a specific, for one of the speakers specifically, please note it in your question. But before that, we'd just like to announce the upcoming GIF webinars hosted by the Education and Training Working Group. The first one will be still in the cyberspace. So in June, we will have a webinar on defensive cybersecurity architecture and its impact on Generation 4 reactors. In July, we will have a presentation by UK&NL on the wider role of nuclear energy systems and the engagement and education activities allowing to enable this role. And in August, we will have the winner of the Picture Gen 4 research competition that was organized by GIF. And she will be presenting on diamonds, who are reactors' best friend, on novel sensors to investigate high valency actinides in molten salts. So to register to those webinars, you can go on the GIF public website, and the webinar in June is already open for registration, and the one in July and August will be open soon. One last point before we move to the Q&A session. If you want to find the recordings and presentation of all the past webinars, as well as the links to register to upcoming ones on the GIF public website, you should go under events and resources at the top of the website, and then go to webinars. And then once you're in the webinars section, you can either see the cards of each webinars already displayed and filter them by topics or year, or you can click on the here that is at the left in capital letters, and this will bring you to a summary table that will show you all the webinars. But with that, I would like to thank our presenters and moderators, and ask our moderators to start the Q&A session. Thank you.
Yeah, thank you very much, Alexei, and thank you to our three panelists for this comprehensive presentation. I hope you had time to drink some water because it's a lot of talks. And we're going to start the Q&A. I saw a few questions related to where can we get the slides? Can you send us the slides? Again, this webinar is being recorded. It will be available on the GIF website. It's archived, and all the webinars are archived on the GIF website. And you have access to not only the recorded webinar, but also to the slides. So have a look at www.gen-4.org, and you will get access to all the slides. I saw a question on certificates. We used to send certificates. I'm not the chair anymore of the GIF Education and Training Working Group, so I leave it up to Dr. Anju Kim to decide if there will be certificates. I'm sure Alexei will ask to Anju if they would be able to provide a certificate for this particular webinar. So with that, I'm going to start with the first question. It seems that you answer, Khalik, but in Hany, but I believe we do not see the answer. So I'm going to read it. Hello, we already have codes to determine nuclear fuel burn-up, boiling time of spent fuel in wet storage, and design of cask for transport of wet fuel to dry fuel storage. Do we need to develop new codes for the Gen 4 nuclear power plant? Thank you.
So do you want me to comment on that?
Yes, because he's asking if we need to develop a new code for the Gen 4 nuclear power plants.
Okay.
It's the first question, Hany.
Okay. I did try while the other presenters were giving their talks go through and provide answers. I'm wondering if everybody can see those answers or not.
No.
Oh, interesting.
That's the reason I'm asking.
Oh, okay. That's strange. I had actually one person say thank you in response to the. So they can't
Because
see.
he's the one.
The answers can be seen in the answered list of questions, but
Okay.
yeah. But if you want to maybe give a short answer live.
Yeah, sure. So what we were saying here, I think this one was talking about the burn-up analysis, if I'm not mistaken.
Yeah.
Yeah. So the goal here is not to replace existing methods. As I said, it's all about establishing confidence, and you can defend that. So scientific way for establishing confidence. So, and we want to talk about situations where we don't have experience. Okay, so we're definitely not replacing what's currently there. Like we have done some analysis on burn-up for sure. There's already methods to do that, but we were also asking questions. Can we learn about the irradiation history? Like the power history or the void history? Can we define some signatures or indicators of that? So research showed that yes, there is some information there that can be recovered from discharged isotopics about that, and can be also used as a verification for the existing indicators for burn-up. And as I said, we compared two different labs independently looking at a sample, and they got different results using existing methods. So this serves as additional indicators, that can help verify or resolve disputes. So do we need something for advanced reactors? I think we don't have enough experience yet. So the question of validation is always, do you have enough concrete experimental evidence that you are going to cover all the uncertainties in your model at the operating conditions? We want to see how those uncertainties will manifest in the application conditions, but we cannot reproduce all these situations in the experimental domain. So we need a way to condense, the information somehow. And I believe the recent advances in physics, coupled with computer power and machine learning, can help us narrow down, what it means to talk about coverage, uncertainty coverage. So think of all the things that you don't know, okay? Parameters, let's say, or some model deficiencies. How can you build experiments that are sensitive to those sources of uncertainties? And when do you know for sure that you have already covered them? When can you stop? What would be a good criteria to say that I've covered 90% of the uncertainty, so that's good enough for me now? Instead of saying I'm hired an expert and he thinks this and that, and experts, can have differing opinions, and some can add more uncertainties. And when you're not sure or you see a dispute, then you have no choice but keep adding uncertainties on top of your problem. So I think we will need the current efforts can continue. People can develop their own tools, but what the center is trying to say is we need a way to compare methods, or say this method, is being performing as expected. This method is missing something. So it's a way. Think of it as how we use Monte Carlo to judge different transport models. Everybody writes their own neutronic transport model, but Monte Carlo is used as a gold standard. So we're thinking using information theory can serve as a gold standard for comparing methods. Thank you.
Yeah, thank you very much, Hany.
Okay.
It's you, Alexei.
Yes. Thank you, Patricia. I also would like first to thank our three speakers for excellent presentations. They're very interesting ones. So it's also reflected in the questions that I've been here in the Q&A session. The next question is to Shahab, and I will read it. So which companies or institutions in Europe are doing research on use of, I guess it's minor actinides in fast reactors? Rosatom has just now extracted some fuel from a reactor and will study it once it's cooled down. I'm aware that INL did such a work a long time ago, but nothing in recent years. Thank you.
Yeah, thank you very much for the question. So specifically in Europe, a lot of the work that's still continuing is in organizations like CEA, is doing work on oxide fuel with minor actinides and fuel performance studies there. We're aware of SCK-SEN, of course, through the MIRA project with the development of the ADS type reactor, and their studies on potentially transmutation of fuel with minor actinides. So they're working on that as well. Of course, European Commission Joint Research Center, JRC, they're also quite active in this domain and kind of developing and testing different minor actinide bearing fuels. And various European projects that are done under the framework of SNI, ESN, II, that kind of supports this. On the NEA side, of course, we have lots of work on this that we've done recently now with the great interest, renewed interest, let's say, in recycling, reprocessing activities in the past year or two. We're also increasing a lot of our activities. We have a task force to explore the fuel cycle closure with transmutation of minor actinides. This report should be coming out hopefully later this year, which is a large effort from our European colleagues, but also not just them, but also colleagues from Japan and the US. And essentially looking at the roadmap on what is required for us to get to a point where we're closing the fuel cycle. When I say this, I mean with the inclusion of minor actinide transmutation. So this is a very thorough roadmap looking at the current gaps and how, the very concrete steps as we go towards kind of the demonstration of these techniques to burn fuel with minor actinides, and how to test that some of these techniques and demonstrate them. Thank you.
Thank you very much, Shahab. The next question is: there's value in developing agreed nuclear taxonomies to help align engagement with AI tools. So since we don't have any specific question for a specific speaker, I'm asking every one of you. Maybe Shahab, you can start, because I know you are working on the taxonomy for molten salt reactor.
Yes, absolutely. So, of course, on all fronts, all we hear from regulators, developers, and everybody is the need for standardization. When people are reviewing safety documents, design documents, any kind of regulatory work, or just even developers, they're faced with different uses of terms for the same language. We saw this, as Patricia mentioned, this is very, let's say, apparent and obvious in domains such as molten salt reactors, where you have liquid fuel, which is completely different from existing designs. And the language that's used is kind of all over the place in different national contexts, different designs. So we've had a major effort with our colleagues at the IAEA and the European Commission to work together to develop a taxonomy and a terminology set that can be helped both with the developers and designers, but also on the regulatory side. And of course, the same can be applied across all novel, innovative technologies, such as AI and machine learning as well. Part of the reason why we're doing or establishing this community of experience and expertise through the AI Expertise Project is exactly that, to bring people from different backgrounds, different domains, and have them participate in the same project. And through this, a lot of the language ends up aligning, and a lot of the terms that are used end up aligning with regulatory awareness throughout the entire project, because we're looking to have regulators participate as well. So all of this is a kind of a major effort to align, let's say, taxonomies and terminologies, not just for on the AI machine learning side, but also on our advanced fuel side as well. So it's a very important effort to standardize these things. So thank you for the question.
Yeah. Thank you, Shahab. Hany or Pavel, would you like to add something? Nope. Okay. So
Oh yeah, sure. No,
please, Pavel. Sorry.
Yeah, I think it's a great question, and I think having taxonomy developed like this will be very, very helpful. There's another use for this taxonomy development effort. It might be a good neutral reason for commercial vendors to come together, because we're seeing a lot of hesitance for commercial vendors because of the competition and proprietary nature of their efforts to work together. But working on taxonomy, I think it's something that they might agree on to collaborate.
Yes. Thank you.
Thank you. We go to the next question. And I think it's to everyone, to all. So several research reactors have been closed in recent years. Which capabilities of such are today and may be expected to be of highest and unmet demand in the coming 20 years? So is there someone who wants to answer that question, to take that?
Maybe I can start off the answer if it's okay. What we're seeing, on the NEA side, this is very much kind of a concerning thing going forward. The loss of, let's say, research reactors, shutting down of research reactors, and specifically as we move towards more advanced designs and advanced fuels, there's going to be greater need for things like high flux irradiation capabilities to help us with fuel qualification, material to be able to, let's say, simulate material aging. And this is going to be really, without these kind of reactors, it's going to be much more difficult to do these things, especially as we don't want these to become, let's say, a bottleneck for fuel qualification. Additionally, all kinds of advanced fuel testing, irradiation loops, sodium, let's say, or gas or lead, these to be able to simulate, again, high burnup, or to be able to get post-irradiation evaluation of some of these irradiations that we do, again, to support the deployment of Gen 4 and advanced fuel reactors, both to support, as I mentioned, SMRs, but also AMRs. And very, very importantly, what's being lost is not just the physical reactors, but also the skills and the know-how, both on the kind of operator side, but also on the regulatory side and the experimentalist side. And these are also very important and valuable skills that are going to become more and more important as we look to kind of expedite the deployment of these advanced technologies. So these are kind of some of the things that we see in the next 20 years. A lot of the private vendors, reactor designers, are looking towards the model where they develop their own demonstrator tools. But of course, it's much better to have these centralized approaches where multiple groups and research can benefit from it, not just, let's say, private industry. Thank you for the question.
Thank you.
Thank you. Anyone else to add to that? Hany or Pavel? Maybe just to give some numbers, I remember IAEA published a nuclear technology review a couple of years ago. I think it was 2020, just to put the numbers behind. So in fact, I remember there was a number of something like 560 research reactors and critical assemblies that have been shut down up to the 2020. But still, there are more than 250 research reactors and assemblies in operation now in the country. So I believe that there is still a big potential that can be used for the advanced reactor technology development.
Thank you.
Thank you. But I think we go to the next one.
Yes, the next one, as I said, for the attendance certificate, we will see with the chair of the GIF Education and Training Working Group if she can deliver some of these certificate to all of you. So Alexei from the GIF Technical Secretariat as the action item, and we will provide, if we can, a certificate. I fully understand. So next question from Sylvia from Kenya. How can AI-driven platforms be designed to effectively support training and mentorship in the nuclear sector while ensuring the accuracy and reliability of technical knowledge shared? Anyone?
Well, let me take that and start the discussion. So in terms of second part of the question, whether there are best practices,
which I did not read.
Yeah,
I did not read.
No, I think AI is too early in development for us to talk about something as a best practice. So I think we're learning how to practice AI at this point, but eventually they will emerge. But the first half of the question, we see a lot of value in taking currently existing simulators. International Atomic Energy Agency has quite a good collection of broad scope simulators, and we take advantage of those. And also power plant-like, very detailed full scope simulators developed by vendors for major nuclear power plants, for example, like JC Systems developing them. If you integrate that with AI, and that becomes quite a powerful learning tool for both operator training and general educational purposes. You can bring VR, virtual reality capabilities to that. It's still emerging technology, but I think it has a tremendous potential in that regard.
Thank you. Thank you, Pavel.
If I may add something here, just wearing the hat again of the academic center that we have at Purdue here. What we're really worried about is that AI will always give you an answer, but it can be confidently wrong. So what do you do about that when you're working with trying to use it for training and mentorship? So there has to be some human in the loop validation early on. Yeah. As Pavel said, it's still early. I don't think it's ready right now, but there has to be some level of validation, explainability, and whatever it's being trained on, it has to be curated in some way and already approved to be used as for fine tuning. Like we cannot rely on tools that scrape the internet, for example, to just build those LLM models. It has to be a very well audited process. And as I said, we need that concept of uncertainty. AI right now never says I'm wrong. Only when you ask it, you tell it you're wrong, and then it apologizes for you. So we need some kind of a confidence scoring or an uncertainty awareness of the way it's generating an answer. It could generate an answer, but it needs to be telling you that, hey, I'm missing certain information. I don't have it. I had to extrapolate it. So it gives you some guidance on where it's falling short, so that you know how to take what it's saying with a grain of salt, as we typically say. Thank you.
Thank you, Hany.
Sorry, I'm just trying to turn my camera on. Yeah, the answers were mostly covered by my esteemed colleagues, but what I can also mention on the expertise, from the expertise side, a lot of the work that we're doing for the data sets, for example, let's say the Holden data set, is to establish this RAG models on top of these data sets. And by developing strong evaluated data, but also strong metadata, it allows for users to directly interact with these very complex and previously inaccessible really data sets, and you can, it doesn't necessarily do strong inference, but it allows you to go through the data set in a text-based style where you can interact, and essentially you can kind of see it's not exactly your traditional training, but you can talk to the data, let's say, and that's sometimes for me I find a very good way to help learning through kind of interacting with the different types of data sets. Just wanted to add that as well.
Yeah, thank you, Shahab. Alexei, next question.
I think the next one is referred to the previous one from Sylvia, so it's just basically the same. We can, I think, skip that because it is related. It has been already answered. So I will go to the question of Mehmet Mubult. I'm sorry about that, but any of the presenters can answer, so it doesn't make any sense to me.
Yeah.
So we go to the question of Johar Mohammed. We'll read it. Dear organizers, thank you for the webinars. Well, I think when I read that, it's about the question about accessing the recordings. I think it has been already explained by Alexei how to, or we will probably say it once more at the end, how to get the recordings of this webinar. So I think this is also quite easy to handle. The question from Li Huang Sang Fan. The presenter mentioned support for organizing courses and international schools on AI applications and nuclear energy. If we wish to host such sessions, what steps should we take? We are currently planning to organize an SMR school in Vietnam this summer with the support of IAEA and PSS. Would it be possible for us to collaborate with GIF International Forum on this initiative? So maybe it's more question to GIF Secretariat and to Patricia.
Yes.
But
yes,
any of the
it's
presenters
more.
can answer.
Yes, like I said, it's more a question that need to be talked through the GIF education and training a working group. So we will bring that to the next. We have a monthly call. I think this is something that Alexei can add on his list, on his action items. Am I correct, Alexei?
Yes, absolutely. And also to the person that asked this question, I'll answer by putting the secretariat email, and you can write us an email with a more detailed proposal, and we can bring that to the Education and Training Working Group and the GIF Policy Group if needed. Thank you.
Yes, thank you so much, Alexei. Next question is the role
maybe
of...
Patricia,
yes,
maybe I may add to that as well.
Sure.
So IAEA, in collaboration with the Collaborating Centre at Purdue, organizes or has developed a curriculum for 1 week school on AI and machine learning that we did
Very good.
Last year together with International Center for Theoretical Physics in Trieste in Italy. I think, Hany, you didn't talk about that in your presentation, but the curriculum is completely developed, and it includes theory as well as practice training, and we will be happy to discuss the possibilities of hosting, or just like if you say that you are looking for such courses and you're ready to host that, just send us an email and we will discuss that as well. So I think, Hany, if you can add a few words about that.
Yeah, absolutely. We try to do that yearly. Last year was really a great success. We got a lot of interest. I think over 300 applications. So there are too many things going on, so you can imagine. So we still want to do this year, and we're hoping that we can do it in the fall, but we have not really finalized things yet. But and I'm still looking out for instructors. We like to, have different instructors every year to bring different perspectives. So if anybody is interested, please reach out either as an instructor or as a recipient of this course. And if you would like to, work with us on the logistics, the site selection, etc., for where this can be delivered, please reach out. We are at that phase right now of making those decisions. Thank you.
Yeah, that's very good. And to all the audience, you have access on the slides to the email address of Alexei, of Hany, and the other panelists. So feel free to reach out to them as well. And to Alexei and Hany, we're happy also to, I will say, publicize the school and the summer school. So let us know. We're happy to help you as well to advertise this kind of event. So the next question is about the role of AI and machine learning in accident management. So whoever thinks can answer.
I can speak of our early efforts and what we hope in AI eventually will be capable to do. But just like Hany was mentioning, it's very, very early. And validation, training of AI, in many ways, it's like you have it at early child development stage, and the expectations is very high, potential is very high, but mistakes certainly also quite possible. But one of the things that AI has tremendous potential to do is for advanced reactors, once data become available and it can become trained properly to assess what can go wrong and provide advice on multidimensional, very complex data sets once they become robust enough to tell, okay, you have this advanced reactor, what would be the safety case and what would be the safety case for licensing for them? That's one side. The second side, during the actual accident and accident management, certainly AI has a potential to assist in robotic platforms with the same purpose, to analyze data and potentially reduce exposure of humans to radiation environments, make them safer for emergency responders and their teams, animals assisting in rescues in particular, because they are much lower to the ground and they get harmed more in radiation environments. It's an early development, but it has tremendous potential in all of those things.
If I may add something here again, from mentoring perspective, like if you're trying to understand, you're a young engineer and you're trying to understand accident scenarios, I have been delivering a course this year here at Purdue, and I'm trying to use AI more in the class instead of saying, asking the students not to do it so that they don't cheat or all that. In fact, I think it's inevitable that this will be a tool for everybody. So it makes sense to invest in it. So anyway, if you look at AI back in 2022, when the first LLM model came and you ask questions, it's simply like a query tool. It's just an efficient way of recalling data that's online, which could be wrong. But I think in the recent years, we're seeing a more integrated query where you can rely on running a model and then query the results or analyze the results. So I see that's where the direction of the AI will go for things that are critical, like safety analysis, where you can couple the LLM model with an actual physics simulator that's looking at a very different situations, and you get some results, you change a few things, you make some decisions, you look at the results, and then you try to work with it to analyze and develop an understanding of why something overheated, for example, or overpressurized. So I see a lot of value in that for safety analysis and for design as well. It's just the ability to interact with it as an infinitely patient teacher who can also run a simulation and tell you what's going to happen, not just query data from some log. Thank you.
Thank you, Hany.
Okay, is it my turn, Patricia?
Yes, it is.
Yeah. Okay.
Unless Shahab wanted to add, you wanted to add something?
Yes, I would.
Nothing further to add from me. Thank you.
Okay.
If I may also add to the previous question, accident management. You know that during the accidents or severe accidents, especially, you may lose your instrumentation, or your instruments may become faulty, or may become, I don't know, noisy or something. And this is something where probably AI might be useful just to test or just to demonstrate you that your signal is getting noisy and reconstruct that, or just simply telling you that signal is false. So that's already will help. But it will require, as many people already said today, that it will require verification and trust in the AI methods that are behind. But I'm pretty sure there are some really some interesting applications also in the area of accident management. So next question is a Halden 2 reactor, so a new version. What type it be to best suit the coming 50 years? I think if we talk about the Halden, it's a question to OECD primarily, but also any other panelist can answer. So please go ahead.
Maybe I can start. So it's a good question. Good to have these kinds of visions. I think ultimately it needs to be about flexibility and versatility. It needs to be high flux. It needs to be able to support advanced designs for sure. In the next 50 years, this is something that will be definitely needed. It would be good to also support thermal fluxes as well, if possible. Of course, not just for fuel testing, it'd be excellent for material testing, to have, as I said, advanced loops, to have hot cells for post-irradiated examination on site. And of course, one thing I didn't mention in my previous answer, but one thing that's also diminishing, as Alexei said, with the diminishing of the research reactors, is also isotope production capabilities in research reactors. So that would be an added caveat if that can be done as well. That, I guess, would be the ideal set of things it can do. But most importantly, to remain flexible and robust, to be able to support various designs that will be coming its way. Because as we see going forward, when we look at, let's say, the SMR handbook and some of these designs, there's the amount of versatility in designs from solid fuel to liquid fuel to all different types of advanced reactors. It will require a very flexible testing rigs to be able to support as many of these designs as possible.
Thank you, Shahab. So again, the certificate will do our best, and Alexei has that on his list. So the next question is about large language model, LLM, require millions of examples to train the neural nets with. There simply aren't that many real-world examples. Setting up millions of simulation to try and create such data also does not appear feasible. Is it really realistic to be able to train an LLM?
I think I can take that one. So I want to distinguish here between two things. And an LLM model is a query system. Think of it as a query system, a smart one. Okay. So you give it some question and it tries to look into a database and tries to find, the most related topics to that, and then gives you a structured answer. But the simulation side, that's you're really running a model and you're looking for a real-time response, like a time series response, a scalar field. LLM models are not yet designed for that. Okay. Before LLM breakthrough came out, we used to think of AI mainly as like a surrogate, model for, or a machine learning model for physics models. But once LLM came over, now everything AI is mostly focusing on the LLM side and took the spotlight away from the physics. I still don't see, a coordinated effort to try to bring the two together. But I think that's ultimately what we need, is that how do you query, but based on simulation results? I agree with the question insight here that you cannot just train it based on infinite number of simulations. So LLM is using what looks like infinite number of points, billions or trillions of parameters, because that's just the model they use to describe the language. But describing physics is not the same way. I mean, we have some of the analysis results I showed you earlier for working with a fuel vendor. The model has like 100,000 inputs, right? But in reality, it can be described maybe by 10 effective dimensions. So we have to revert back to the concept of reduced order modeling, pattern recognition, things like that, before going to blindly train those. We cannot train them in the same way an LLM text model is being trained. So it has to be different criteria. And we already have a wealth of knowledge from statistics and applied mathematics that tells us how to find patterns in very large amounts of data. A lot of research happened in the last 20 years on that. So that needs to be the basis for building those machine learning models to analyze physics. And then you couple those with the LLM models. Thank you.
Thank you, Hany. Someone wants to add something? No? So maybe
last question. I can say please. Something quick. Just to add to Hany's response. So in terms of LLMs, you don't necessarily have to train the LLM yourself. You can use, we've seen work where an LLM, you can already use an out-of-the-box trained LLM and put on top of it a RAG model, like a retrieval augmented generation, where now you kind of are doing this transfer learning where the LLM is already trained, but not on a data set that you're necessarily looking to interact with. But then by the application of the RAG model, you can use a model that's already been trained on, let's say, language, and then apply it to your data set. This improves your accuracy, it reduces hallucination, and it's essentially in its improved querying method where you get to interact with the data directly. So you don't necessarily have to train the LLM yourself. There's plenty of people that have done great work in models that already exist, like Llama, GPT, etc. These already exist, and they can sometimes be used directly out of the box to just use their weights and apply it to your own use case.
Thank you, Shahab. Last question, I guess, Alexei.
Thank you. The last question from Luca Volontario is also referred to LLMs. When we talk about using LLMs in nuclear applications, there is inherently non-deterministic systems. They can give different answers to the same input. Are there any standards or frameworks currently being developed to address this? And on the explainability side, how do we actually demonstrate to a regulator that the model's reasoning is trustworthy, given the tools like, I think it's Shapley additive explanations, or attention maps are not formally validated yet? So whoever can take that question, please.
Well, I think we probably all can chime in. So let me start and just quickly say that this is an active research area. I think there are many groups working in exactly those type of questions. At the same time, I don't think the task is really to demonstrate trustworthiness. When you submit something to, for example, a regulator, the assessment is on the technical validity of the answer. Not whether the answer is trustworthy. So it's a little bit different than assessing whether you can trust the answer. And from that perspective, it becomes manageable. Otherwise, you cannot really use it for any kind of practical application. But this is the same true for humans when you have human experts. The same would apply to a human. And we use humans to assess reactor safety since the beginning. And that really ages-long old question to answer. But it's an active research area, so we're all working in that. And I think it gets better with time. But
So I can also weigh in on this one. When you write an equation, again, looking at this from the information theory lens, when you write an equation like Boltzmann equation or the Bateman equation, that's a clearly defined constraint on how things move. Okay, and that establishes a clear PDF or an uncertainty distribution for the quantities that you are after. Okay, so through the information theory lens, you can make very strong statements about what is the uncertainty you should expect in solving these equations. If the source of uncertainties are parameters, initial conditions, whatever. Okay, but that's from the physics perspective, which we really understand. But when you go to the text world, the LLM world, and the way the embedding works, there's no physics there. It's simply a clever way to describe how words come together. Okay, they're trying to pretend that there is a PDF that describes how the words come together. It's very clever and very efficient, but it doesn't have a physical meaning to it. So it's always going to be subject to things that don't make sense. Okay, I mean, think of a young child when they're starting to learn. You know, they hear words, and sometimes they put words together that you did not think about. Okay, what, and to you that would be like hallucination, but they put them together because in their mind they have a PDF. They heard a lot of words from their parents and their family, and then they thought maybe these two words should go together. LLMs can do the same mistake. So you can always devise methods, you know, rigorous methods to just, or let's not call them rigorous, procedures just to validate what the LLM is coming up with. But I don't think you'll be able to eliminate completely. So we cannot turn this into a fully autonomous, whatever is coming out from the LLM model should be trusted. It has to be always a human involved to validate, especially for high consequence systems like a nuclear reactor.
Thank you, Hany. Thank you, Pavel.
Maybe I can just sum it all up. Of course, I'm in complete agreement with what Pavel and Hany have said. But just to add that this is, again, to reiterate, a very active research area. Many of the universities we spoke with are actively looking for ways to evaluate LLMs and how they operate again in different domains. And it's actually one of the benchmarks that we're looking to consider in the expertise because of the large amount of interest. And we're essentially looking for clever ways. There's already some universities doing this to benchmark how LLMs perform and demonstrate, how they do with different types of within different types of domains. But of course, as Hany said, at the end of the day, there is no test of let's say, a fully validated way to say this is exactly will always give us the right answer 100% of the time. And so, we're just trying to evaluate which LLMs work best in which domains, but it will not ever replace kind of the human in the loop at the end of the day to agree and finalize the decisions that are being made because of the potential for mistakes at the end of the day.
Thank you, Shahab. So, Alexey, I'm turning to you for concluding remarks, and then I will finish up the webinar.
So, I think we finished. We're done with questions, yeah?
Yes.
All right. So I think that was very interesting from my perspective. So I'd like to thank every participant, our panelists, Patricia, and all behind the scenes, because this is also very very important. And give the floor back to Patricia for concluding.
Okay, so I would like to thank everyone, the three panelists, for your time. Alexey, thank you for helping me moderating this webinar, and the GIF Technical Secretariat, especially Alexey, for making that happen. You see, it's 7:37 a.m. for me, so it's more than 2 hours for a webinar, and we still have 122 attendees. We were at a max around 250 participants live, so unbelievable, a very hot topics. I thank everyone who asked questions. Again, it will be posted, archived the webinar on the GIF portal, as well as the slides. We'll look for the certificate if we can deliver. Thank you to everyone. You have the email address of the presenter. This is a very, very important topic. Thank you, Hany. Thank you, Shahab. Thank you, Pavel, for really volunteering and to present and to participate. Thank you again, everyone. We wish you a good day, a good evening, and next webinar on the 22nd of June, if you have time. Thank you again, everyone. Thank you.
Thank you.
Thank you.
Thank you, everyone.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.